Welcome to UV Physics Academy. So here we are discussing quantum algorithms. In this sixth part, I'm going to discuss about Bernstein-Vazirani algorithm. So what is this algorithm? So for example, here we have an unknown function f of x, which is defined as f of x equal to some a dot x. What is a? That a is the hidden variable. A is the hidden variable. And what is that dot? So this dot product is the bitwise binary dot product. Bitwise binary dot product. So what is this bitwise binary dot product? Let me give one example. So for example, if you have x equal to x1, x2, x3, I have taken 3 qubits, and y equal to y1, y2, y3. Then what about this x dot y? This is a bitwise dot product. Okay, take this first qubit and first qubit, that is x1 y1 plus x2 y2 plus x3 y3. After that you have to take a mod 2 operation. So let us take one more example here. So here I have 110 dot 101. So simple, take the first qubit and first qubit, that is 1, and a second qubit and second qubit plus 0, third and third, that is also a 0. Here it is 1. After taking taking this mod 2 operation, here we'll get a 1 only. If I take a 111 dot 110, so then if you take this dot product, so this is 1 plus 1 plus last one is a 0, because here 1 into 0 is a 0. Here this is a 2. After taking a mod 2 operation, you will get a 0. So finally you will get either 0 or 1 always. Okay, fine. That's why bitwise binary dot product with modulo 2 operation. Now again, okay, come back. Here what we are finding, what is our aim? So here our aim is to find a. So what is a here? Hidden variable. So how to find? Let us recollect what we have done in the DJ algorithm. So in DJ algorithm, what we have done? We just check whether the output we are getting 0 or not. That's it. So here we find whether the output equal to 0 or not. Okay, actually what we have done in that, so we have an unknown function f of x. We don't know whether it is a constant or balanced. So first we have assumed that f of x is a constant. Then we got the output is equal to 0. There we find the probability of getting output is 0 as a 1 if f of x is constant. So of course if f of x is balanced, already here we got the probability 1. So that's why definitely the output is not equal to this is 0. Okay, right. So now in this algorithm, that is a Bernstein-Vazirani algorithm. So what is the specialty of this algorithm? There we find, or there we check only whether the output is 0 or not. Here we are getting finally the output equal to a. So here we are going to find the output equal to that a hidden variable. So here we are getting the complete output. It's not just checking whether the output is 0 or not. Here just finding the complete output as a, which is a hidden variable. So this hidden variable is defined like this: f of x equal to this a dot x. Okay. So let me take the circuit. Okay. Wait. Right. So in this BV algorithm circuit, okay, so here we have this 0, okay, so n number. So parallelly we are having that zeros states, qubit states, and these are head mod operations, that is n number of head mod operations. And here we have one, so single head mod gate, and again here also we have n number of head mod operations, and here we'll get a minus because h1 will get a minus. So here the function f is defined as a sum a dot x, and our aim is to find this a. That means here if you make a measurement, so here if you make a measurement, here we have to get an. So let us check whether we'll get this or not. Now in this algorithm also we are using that most important feature called uh, phase kickback. Okay, so let me take that phase kickback. So here we have x minus, this is the UF, that means a unitary operation. So the information will transfer from target register to data register. So minus 1 whole power f of x, x minus. Now in this algorithm, we are taking f of x as a dot x. So that's why this x minus input, what is the output corresponding, minus 1 whole power a dot x, x minus, where a dot x is the bitwise binary dot product with a modulo 2 operation. Okay, fine. So now let us start this algorithm. So here what is the input? Here we have h tensor n operates on 0 n qubit string. Okay, so again h1, this is nothing but, so we have already discussed in the parallelism concept. So this is nothing but 1 over root n summation x, where x is equal to 0 to n minus 1, and after that this h1 is nothing but minus, right? Fine. Okay, now we are operating this uf, this unitary operation. Okay, so here we have already this phase kickback result, just apply that. This is nothing but 1 over root n summation minus 1 whole power a dot x, x minus. So very simple. So this one, this become x1 minus become minus 1 whole power a dot x, x minus. Fine. Now we are going to operate this head mod operations. This is very important. Okay, so here finally let me write what we get, 1 over root n summation, here it is x equal to 0 to n minus 1, and this is minus 1 whole power a dot x, x and minus. Now here on this we are going to operate this h tensor n tensor I. So this identity on this minus state, and h tensor n is on this x. Don't forget this x is nothing but n qubit string. And earlier I have already explained in the quantum parallelism class. So whenever h operates on, I mean h tensor n operates on 0, all zeros, n qubits, this is 1 over root n summation x, uh, x is equal to 0 to n minus 1. But other than 0, for example, if you have h tensor n x n qubit string, here you will get some phase factors. So this is a 1 over root n normalization factor summation minus 1 whole power phase factor. This is nothing but x dot z sub z, where here z is equal to 0 to n minus 1. I have already explained this. I request you, if you don't know, please check this. Now take it and substitute. So this is a 1 over root n summation x equal to 0 to n minus 1 minus 1 whole power a dot x, and here summation over z, one more 1 over root n is there, just I am writing outside, okay, minus 1 whole power x dot z and z. This is n qubit string. Okay, now let me rearrange this summation. So this is a 1 by n. Now here finally here I am getting the linear combination of z. That's why summation over z is equal to 0 to n minus 1. Finally we are writing that as a linear combination of this z. So something that is related to the amplitude, and this is a zn minus. So what is this? This is nothing but summation x is equal to 0 to n minus 1 minus 1 whole power this one a dot x, and after that this one minus 1 whole power x dot z. So this is what we get. So let me write the next page. Okay, so let me explain here itself. Now carefully observe here this one. Okay, so for example here I told you already our output should be equal to a. So now if I take z is equal to a, then I have to get the probability of finding z equal to a is nothing but 1. If I get the probability 1, the output z is equal to a, otherwise it is not equal to a. So let us check. For example, if I take let me write here, if z equal to a, then carefully observe this minus 1 whole power a dot x minus 1 whole power x dot, in this case now z is equal to a. So this is nothing but minus 1 whole square whole power a dot x or x dot a, which is nothing but 1. So this entire summation, sorry, this term is nothing but 1 if z is equal to a. So fine. Now I am going to find the probability of getting output z equal to a. Okay. So then this is nothing but probability amplitude I am finding, of course. So that is a 1 by n summation 1, and the summation is from 0 to n minus 1. So that's why this is nothing but 1 by n into n, so which is nothing but 1. So finally we are getting a probability of finding output z is equal to a is nothing but 1. So uh, in this algorithm we are finding that output which is equal to a, that is the hidden variable. How it is defined? F of x is equal to a dot x by using that binary bitwise binary dot product. Okay, so once you make a measurement, definitely you will get output z is equal to a, which is the hidden variable, right? Right. So I hope you understand what is this Bernstein-Vazirani algorithm. Now I'm going to explain one example for this algorithm. So here I will follow two methods. One is by constructing the oracle, and the next one is by using the phase table. So quite interesting. Second one is very interesting. So I request you please watch that a second method also. Okay. So now let us discuss about this first one. This is by constructing oracle, and here also I am using decimal notation, please remember. So first to solve the circuit I will use the decimal notation. Once I got the result I will immediately convert to binary, that's not a problem. So here let me take the circuit, and here first example I am taking the hidden variable. Sorry, first one, let the hidden variable a as a 1 1. Okay, in the decimal notation it is a 3. Okay, fine. So for that let me construct the circuit, I mean let me design the circuit. So right, so here first I have taken that hidden variable a equal to 1 1. So in the decimal notation I can take it as a 3. So remember, while I am solving the circuit, I will use the decimal notation. So here, how to construct the oracle for this a equal to 1 1. So what is this oracle here? Here total 3 qubits are there. Of course, we are observing here 0 0. So once you make a measurement here, we have to get that output a equal to 1 1 1 1. Okay. Here it is 1 Hermod, and here you will get a minus. Fine. So what is the oracle? Total 3 qubits are there. So sorry, 3 qubit states are there. 1, 2, and here it is. So it is a 1 1. So that's why from here to here 1 C naught, and again 1 like this. Okay. So what is this? In decimal state notation, 1 2 4. Okay. So let me write this operations. This is nothing but x 4 to 1, sorry, 4 to 1 means 4 comma 5, and you have to add 2 6 comma 7. I hope you know this. And x of 2 comma 3, and you have to add 4 now, 6 comma 7. So these two multiply, this is nothing but I 6 comma 7. So now if you observe carefully, what is the unitary operator corresponding to this oracle function? So the unitary operator is nothing but, you can write like this, diagonal. There is no 0 1, that's why identity. And a 2 3 x operation is there, that means 2 and 3 will flip. Next 4 5 x operation is there, that's why flip. 6 7 identity. It's a diagonal matrix I x x I. That's it. Good. Now let us proceed. Now let us solve this circuit. Here we have H tensor 3 operates on 0 0 1. I hope you have attended that quantum parallelism class, and I explained one small technique to write this value. So total 3 qubits are there, and what is the first one? 1. So could you please tell me what is this here? Plus minus. If it is a 1, starts with plus minus. After that 0 came, repeat the earlier as it is. After that 1 you got, then multiply with extra minus. Whatever earlier signs you have, just multiply. So he was started with 1, that's why plus minus. Next 0, plus minus. Next again 0, plus minus plus minus. Fine. So I think I can write this as a 1 over root 8, 0, minus 1, plus 2, minus 3, plus 4, minus 5, plus 6, minus 7, like this. Now we are going to operate this UF, whatever the oracle we have constructed. So we are going to operate that. So please check what is this oracle function. That is x23 and x45. So 2 and 3 flip, and 4 and 5 flip. 4 comes to fifth place, and fifth state comes to fourth place. That means the phase factors interchange. So here we will get 1 over root 8. This is a 0 minus 1. Here earlier we have 2 phase is a plus plus, but now it become minus 2. Earlier for 3 it is a minus, now it become plus. I hope you understand what is the meaning of this. Now this is a minus 4, so plus 5. Just interchange that phase factors. 6 as it is, and 7 also as it is. That's it. Now I'm going to take the head mod operations. So I request you please follow that earlier lecture. So I explained one small technique how to write these operations 1 to 4. Here we have head mod, two head mods. One is on 4, another is on 2. So let us proceed. So what is this head mod operation? So here we have, this is let me take here. Under this head mod operations, that means we have two head mod operations here. So this is a h of 0 comma 4, and after that you have to add the remaining qubit states, decimal states 1, 1 comma 5, and again you have to add that other one 2, that is a h of 2 comma 6 and h of 3 comma 7. If you learn this technique, it's very easy to solve any quantum circuit. Next one, next one more head mod is there, that is on 2. So this is a h of 0 comma 2, control comma target. Here control is not there, that's sorry, uh, it's a single quantum bit, so single quantum gate. So that's why here it is a 0 comma target. 0 comma target is a 2 here, and you have to add 1, 1 comma 3, and again you have to add 4, 4 comma 6, and next 5 comma 7. No cancellation, okay, no common states, that's why no common operations, that's why you can't cancel, leave it. Now how to operate this head mod operations here? So please check, it's very easy, it's very easy. Now here I have 0 and 4, carefully observe 0 and 4. These methods I have already explained in the quantum circuits, okay class, I request you please watch that. 0 minus 4, minus means on. Here what is on? All second numbers are on, all first numbers are off, on, off. So here 0 minus 4, 0 minus 4 is nothing but on, that's why it is a 4. Please cancel this 0, 4. Next, I am taking minus common, then it is 1 minus 5. 1 minus 5, again on, 5. Next, minus common, here I have 2 and 6 combination. You have to go for operations from left to right. Left to right. So here 2 comma 6. So minus common, 2 minus 6 on, that's why 6. Next, I am not taking any common, plus as it is, 2, 6 cancel, 3 and 7. 3 minus 7. 3 minus 7 means again on. So which is on here? 7. That's it. So because it is easy to do this algebra, and finally we'll convert into binary only, no need to worry. So now only one head mod operation is completed. So this one is completed. Now let us go with this second one. The next one, I have 4 and 6 combination, that is a 4 minus 6 on, here which is on 6. Next minus common, 5 minus 7, that is also on, that's why 7. So two states are there, that's why 1 over root 2. No need to bother about that normalization constant earlier. Once you have done the operations, finally if you get left with the 2 states, write 1 over root 2, 1 over root 2. You're left with the 4 states, write 1 over root 4 like that. And now I am converting into binary notation. So this is nothing but 1 over root 2, 110 minus a triple 1. I can take out that common first 2 qubits. So that is 1 1, 1 over root 2. So that is a 0 minus 1. I hope you understand now. This is nothing but 1 1 minus. So just for the solving purpose, I mean for that solving purpose only I used the decimal notation. After that again I can convert into binary. So once you make the measurement here, you will get the output equal to 1 1. This is what we need. Okay, so now let me explain one more hidden variable. Here we have taken 1 1. If it is a 0 1 and 1 1 0, how it is. So let us check that also. Okay, so I request you please remember this first one. Okay, next I'm taking another example, that a hidden variable a equal to 0 1. Still not understanding, so please listen. Now here first let me construct the oracle. So the oracle function here. So this here 3 qubit states are there. So here it is a 0 1. So 0 1 means here forget about this here. This is a 1. That's it. this is a 0, because here we have to get the output as a 0 1. Try to understand. So that's why here this is a C naught operation. Here 0 is there, that's why no C naught. Earlier, if you observe carefully, here both are 1 1, because we need to get the output as a 1. Sorry, we have to get the output as a 1 1. That's why you have taken both C naughts from that qubit states. Okay, right. Now, so here we have only the first qubit is 1, so that's why here we have C naught gate, and the next one is a 0, that's why you need not to take any C naught operation. Now let us come to this decimal state notation 1 2 4, and let me write what is this. This is x 2 comma 3, you have to add 4, that is x 6 comma 7. Once you add 4, it become a 6 comma 7. So what is the unitary operator here? This is a diagonal matrix of order 8. Okay, so here no 0 1, that's why identity. I hope everybody understand how I am writing this unitary operator. Okay, so 0 1 is not there, that's why this is the advantage in the decimal state notation. 0 1 is not there, that's why identity. 2 3 is there, that's why x. 4 5 no, that's why identity. 6 7 is there, that's why x. So this is of matrix order 8 by 8. Fine. So what it will do? It flip, or it will change the phases of 2 and 3, and here also it will change the phases of 6 and 7. Now let me take that initial state again. H tensor 3 operates on 0 0 1, and please remember here plus 1 is there. Now you please try, pause the video and try to do it yourself. Plus minus, and again 0 repeated, plus minus, again 0 repeated, plus minus, plus minus. Now this is nothing or 1 over root 8. So 0 minus 1 plus 2 minus 3 plus 4 minus 5 plus 6 and minus 7. Now I'm going to operate this oracle function UF, which interchange the phases of 2 and 3 and 6 and 7. Then it is 1 over root 8. This is a 0 minus 1 as it is. Second state, 2 state phase change, minus 2 plus 3 and 4 5 as it is, and 6 7 flip, minus 6 plus 7. Right, now I am taking this head mode operations. Already we have taken earlier. Let me copy that. Otherwise, if you forget, let me explain one more time. So here it is h, here it is h, here nothing. So decimal state notation 1 2 4. So what are these what are these operations? Here we have h is on 4 here, so that is a 0 comma 4. You have to add 1, that is 1 comma 5, and again you have this 2, that's why I added 2 comma 6, and again add 2 3 comma 7. This is the first head mod operation, and the next one is on 2, that's why h 0 comma 2. You have to add 1 1 comma 3, next add 4 4 comma 6, and 5 comma 7. Now please apply the cancellation technique. So here 0 plus 4, 0 plus 4, 0 plus 4 means off. See, if you attend the earlier quantum circuit video, definitely you will understand. There is a video how to solve any quantum circuit by using a new method. So 0 and 4, 0 plus 4, that's why off. Here which is off state, this is 0 is the off state. Next one, 1 5. So I'm taking minus common. This time minus common, 1 plus 5, 1 plus 5, that's why it is a 1. 1 plus 5 means off, that's why you have to take 1. Next 2 and 6 combination, again minus common, Again 2 plus 6 I got, that's why minus 2. And the last 3 plus 7 of, that's why plus 3. Next one more head mod operation. So one more head mod operation is there. So this one first one, this one second one. Always you have to go from left to right only. Next 0 and 2 combination. This time 0 minus 2. That's why on you will get 2. Easy, very easy. Minus 1 minus 3. 1 minus 3 means on. So which is on here? 3. So that's why 3. I think head mod operator is operating on that 1 minus 3, you will get a 3. So that's it. Because to do this algebra in the decimal state notation is easy. I feel like that. So you have two states, that's why 1 over root 2. Now I am converting into binary. So this is a 2, 1, 0, minus 3, 1, 1. So you can, 1 minute, I'm sorry. So here you have to take 3 qubits, yes. Yes, because whatever we have written this decimal notation, this is based on 3 qubits. So always better to write like this. That 3 stands for total 3 number of qubits are there. So that is a 0, 1, 0. That is nothing but a 2 minus 1, 1. Sorry, 0, 1, 1. I hope now you understand. I can take out common 0, 1, and after that 1 over root 2, 0 minus 1. So finally I got a 0, 1 minus. Once you make a measurement, you will get that output as 0, 1. So I request you third one, you please try yourself. So third one I'm giving you as homework. So hidden variable here, a equal to 1, 0. Please take it as 1, 0. So try to construct first oracle. Okay. So here first one is a 0. Actually here you have to get the output as a 1, 0. Simple. 1, 0. Here 0. That's why no C naught. Here 1. That's why a C naught operation. And after that, once you understand that, you please apply the decimal state notation 1, 2, 4. This is x, 4 to 1. That's why 4 comma 5. So 2 qubit quantum gates, that is a unitary operator C comma C plus T. Your control is 4, target is 1. That's why 4 comma 5. And you have to add the remaining, that is x 6 comma 7. So what is the unitary operator corresponding to this? This is a diagonal matrix, D for diagonal. 0, 1, no, that's why I. 2, 3, no, that's why it's I only. 4, 5, it is there, that's why X. 6, 7 is also there, that's why it is X. That means it will flip the phases of 4, 5 and 6, 7. So very simple. I request you please try, and finally you will get the answer. Now let me take the another method. This is quite interesting. Okay, just wait. Right. Now here I'm taking another method. This is quite interesting. So phase table. So this also I have explained earlier in the earlier videos. Okay. Right. So what is this a phase table? Actually, this is a minus 1 whole power x dot z, and this table is useful in two ways. This is also nothing but a H tensor 2 operates on 0, 1, 2, 3 like this, 2 qubit states. Okay, so fine. Let me fill this table. Here we have 0, 0. I'm writing in the binary notation 0, 1, 1, 0, 1, 1. Okay, so please observe, it's very important. So here first one is 0, that's why plus plus, and 0 repeated, that's why again plus plus. Here 1 plus minus, 0 repeated, plus minus. Here 0 plus plus, but 1 you got, that's why how to multiply with minus. Here 1 plus minus, next one 1 you have to multiply with minus, minus plus. That's it. So you got phase factors. Now let me execute this circuit. So here first one, H tensor operates, H tensor 2 operates on 0, 0, and next H operates on 1. I'm not combining. Here earlier we construct the oracle. So that's why I combined that as 0, 0, 1, and finally we got the unitary operator and we operated. But we didn't multiply any matrix multiplication uh, like that. But here simply we are using that decimal state notation. Okay, ready. So H tensor to 0, 0, this one. This is nothing but first one 1 over root, sorry, 1 over root 4, all are plus only. Here if you observe carefully, this is a 0 plus 1 plus 2 plus 3, and h1 is nothing but minus. Okay, so let me take here. Now we are going to operate this UF, this unitary function. So what is this operation? X minus, under this unitary operation, this is nothing but minus 1 whole power x dot z x minus. So we will get some extra phase factor here, which transfer from target resistor to data resistor. Okay, so this is nothing but, here our hidden variable is what? Sorry, it's not x dot z. I'm sorry. This is a dot x. I'm sorry. This is unitary operator. Minus 1 whole power a dot x. And in this case, our a is nothing but a 3. So that's why I'm going to write 1 over root 4. This is a minus 1 whole power 3 dot 0. Carefully observe this. Minus 1 whole power, a is a 3, x is a 0, plus next x is a 1, minus 1 whole power 3 dot 1. I'm writing in the decimal state notation only, no need to worry. Minus 1 whole power 3 dot 2, 2, plus minus 1 whole power 3 dot 3, 3. Now please see, what is a minus 1 whole power 3 dot 0? Here plus 3 dot 0, 3 dot 1, 3 dot 2. I hope you are observing. 3 dot 2, 3 dot 3. So these are the phase factors. So finally here we got this one. So this is plus, minus, this is minus, and this is plus. Finally this is nothing but 1 over root 4. Of course here minus as it is. 0, minus 1, minus 2, plus 3. Now carefully see. I told you this table is also useful for finding the head mod operations. That is, a H tensor 2 operates on 3 is nothing but the linear combination of 0, 1, 2, 3 with these phase factors. I hope you are observing. So carefully observe this entire thing is nothing but, it's quite interesting. This is nothing but here I'm writing. Okay, so this is nothing but H tensor 2 operates on 3. Please check. 1 over root 4, 0, minus 1 here, minus 1, minus 2, plus 3. Fine. So that's why this table is very useful. And in two ways we are using this. One is for getting that binary dot product, and another one is a head mod operations. Okay, I'm using for these two operations. So finally here we got H tensor 2, 3, and a minus state is as usual here. On this now I'm going to operate this head mod operations. That is H tensor 2 tensor I will operate on this minus, H tensor 2 operates on this. Again you are operating head mod operation. So H square is nothing but I. So this is not H square, that is a H tensor H means like this, parallel H. And again one more time you are operating like this. Okay, so then this will become I, this will become I hope you understand. Still not understanding, please check. So here this is nothing but, already head mod operations are there, H, and one more time H tensor 2, that means one more time if you take a head mod operations, you will get identity. So this is nothing but a 3 minus state. Now I can convert into this binary, that is a 1 1, 2 qubits minus. Once you make the measurement, you will get 1 1. That's it. So let us take one more example how this table is useful. Right. So here again I'm taking this input, this one, okay. So here it is 1 over root 4, 0 plus 1 plus 2 plus 3, and here minus. Now here we are assuming that hidden variable a equal to 1, that is a 0 1 in binary. So here I'm going to operate this UF, that means, okay. So this will give you minus 1 whole power a dot x minus, okay. So that's why this is nothing but 1 over root 4. This is minus 1 whole power 1 dot 0 0, because here a is 1, minus 1 whole power 1 dot 1, x is 1 here, plus minus 1 whole power 1 dot 2, and here x is 2, plus minus 1 whole power 1 dot 3 3, and after that minus state is as usual, okay. So fine, is it okay? Right. Now please check from this table if you have this 1 plus minus plus minus. So this is a plus and this is a minus and this is plus and this is minus. Okay, so this is a 1 over root 4, 0, minus 1, plus 2, and minus 3, minus as it is. If you carefully observe, this is again, I told you this table is useful for Hadamard operations as well as a phase bitwise dot product table. So this is nothing but H tensor 2 operates on 1, this one, here 2 qubits minus. Now I'm going to operate that again Hadamard H tensor 2 tensor I. So this one, this part, okay. So then I will get this H tensor 2, this H tensor 2 will get identity. So finally you will get 1 with the 2 qubits and minus. This 1 qubit, 1 is nothing but 0 1 minus. Now I convert into binary. So once you make a measurement here, you'll get a 0 1. So I request you please try the another one also. The last one I will take, let a equal to 1 0, which is nothing but 2. So I hope the state, initial state H tensor 2 0 0, H1, you know already, this is nothing but 1 over root 4, 0 plus 1 plus 2 plus 3, and this is a minus. Now with this unitary operator, we'll get the phase factors corresponding to 2. So these are the phase factors corresponding to 2. So which is 1 over root 4, sorry, right. So this is a 1 over root 4, a 0, 1 is plus, sorry, for 2 it is minus, and for 3 it is minus. In this method I am not operating any Hadamard operations because just I am taking from the table, because earlier we construct the oracle and here we are using this phase table. So with this, okay, this is nothing but again this Hadamard operation only. So this is a H tensor 2 operates on 2 minus. So convert into binary, sorry, operate another one more is there, that is a H tensor 2 tensor I will operate on this minus, H tensor 2 will operate on this. So this is nothing but again 2 minus, and once you make the measurement here you'll get 2, that is 1 0. You can write in the binary 1 0 minus, once you make a measurement you will get 1 0. That's it. So now let us take 3 qubits hidden variable, that is some 5 or 6 in 3 qubits. Here we have taken only 2 qubits. Okay, just wait. Right. So here I'm taking that hidden variable as a 3 qubit state. So here 1 came, that's why plus minus, and here again 0 plus minus, sorry, plus minus. Here first 0 plus plus, next 1 minus minus, again 0 plus plus minus minus. 1 plus minus, 1 minus plus, 0 came, plus minus minus plus, 0 plus 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 plus, and again 1 all minus. Next 1 plus minus, 0 repeated, next 1 repeated, so that's why minus plus minus plus. Whatever earlier you have the states, just multiply with minus if 1 repeated. So 0 starts with plus plus, minus minus, and again 1 is there, minus minus, plus plus. Again all ones, that's why plus minus, reverse, minus plus, again opposite, minus plus plus minus. So this is the phase table. And as well as head mod operation, this H tensor 3 operates on 0 1 2 3 like this. Okay, fine. Now here I am assuming that a hidden variable, let a equal to 1 0 1, so which is equal to 5, 3 qubits. Okay, so as usual let me proceed. This H tensor 3 operates on 0, here we have 3 qubits, and H operates on 1, which is nothing but 1 over root 8. So here you will get 0 plus 1 plus, here I don't, all are plus only, that's why I'm writing like this, plus 7, and next minus. Now once you operate this UF, this will become x minus, under this unitary operation, minus 1 whole power. Here our hidden variable is a, let us say a dot x, x minus. Okay, so this will give you minus 1 whole power 5 dot x. So please check where is that 5 here. So directly write this. So finally we will get 1 over, sorry, after this unitary operation you will get 1 over root 8. So here the phase factors, first one is plus, next one is minus, and again plus, carefully observe, next minus, next again minus, next plus, next minus, and next plus. And here finally this minus state is as usual. Now what did you observe? This again, this is nothing but H tensor 3. H tensor 3 operates on 5. That's it. So this is nothing but H tensor 3 operates on 5 from this table, if you can observe. And minus. If you have any doubt, just operate earlier how I explained that decimal state notation, how that head mod operations. Please write the head mod operations and cancel the states. Finally, you will get the same answer. No doubt about it. H tensor. Okay. So this is nothing but H tensor 3 5. Oh, 1 minute. Yeah, right. So H tensor 5 and next minus. Sorry, H tensor 3 operates on 5 and minus. Now here we have this operation, this one. So here this is H tensor 3 again, tensor I. So the I will operate on this minus as it is, and 3 head mod operations, and again parallel 3 head mod operations. So everything, I mean, it will become identity. So you will left with 5 again. So now if you want, you can convert into binary, that is a 101 minus. So once you make a measurement, you will get 101. So here I don't know whether this is the right method or not, but it is easy to understand what is happening with that oracle function. That is what I'm saying. This table, phase table will help you what is happening. So how we are getting that phase changes. That's it. Okay, so fine. And you can try the another one, a equal to 6 hidden variable or 7, anything. I hope now you understand. If you take 6, you will get this one after applying unitary operator. And again, that is nothing but h tensor 6, sorry, h tensor 3 times on 6. And again, you are operating the head mod operations, you will get the 6 output, that is 110. Okay, so I request you, please try yourself another one. Let us try another one, a equal to 110, and another question, a equal to 111. Okay, so if you want oracle, I will tell you how to construct also. If you want oracle for a equal to 101, so here we have 3 qubit states and here the last one. So we want to get 101, okay, right? So that's why in the middle there is no C naught. Here is C naught and the last one is C naught. Okay, that's it. And if you want the oracle for 110, so 3 qubits and here the last one. Careful, 011, because this is the LSB in my decimal state notation and everything. So that's why here it is a 1 and here 1, here 0, that's why no C naught. And if you have a equal to 111, so I hope now you understand. This is nothing but, and what it will do, 1 2 4 8, this is also interesting. So this will x 8 comma 9, x 4 comma 5, x 2 comma 3, and all are on. That means here C naught gates. 8 plus 4 plus 2, that is a 14. So that is a x 14 comma 15. So there is no 0 1. So you will get this unitary operator as a diagonal matrix of order. So this is a 16 by 16. I think, yeah, 16 by 16. So this is a 0 I, next to 2 3 x, 4 5 x, 6 7 I, 8 9 x, 10 11 I, 12 13 I, 14 15 x, like this. Okay, so this is a 16 by 16. Like this we can construct the unitary operator also. Right. So this is the conclusion of this PV algorithm. This is my point of view. Okay. I'm not sure whether this way of explanation is right or wrong. Okay. If any correction is there, I request you please let me know. Okay. Right. So here we got H tensor 3 operates on this 0 0 0 and H1. So because if you see carefully this circuit, this, I'm taking that input. This can be written as, this is a H tensor 3. I'm taking a decimal state notation, 3 qubits, and this is a minus. Now carefully observe. Now here you are operating this unitary function, that oracle whatever we have. In this case, I am assuming the hidden variable as a equal to 5. Then what will happen, after this operation, this 0 is replaced with 5. If you observe carefully that earlier algebra, whatever we have done, you will understand. Take the linear combination and apply the phase factors, you will get again H tensor 3 5. Okay, so that's it. And after that, the final operation, this one, again you have to consider H tensor 3 tensor I. Okay, so already we have 3 head mod operations here due to that oracle function. After that, again you are applying 3 more parallel head mod operations. So that's why you'll get identity. So this will become 5 3 qubits minus. Now please convert into binary, that is a 101 minus. Once you make a measurement, you will get the output as a 101. Okay, so let me write more generally. So what I am assuming is, more generally, let us write in a single line what is this BV algorithm. So here we have, I am assuming A equal to some Z, the hidden variable, 7, 6 or something, whatever it is. So n qubit string. So then it is H tensor n operates on 0. This is n qubit string, and H1, okay, this is nothing but H tensor, okay, the same thing, no issue. Okay, let me write here H tensor n 0 n minus, super. Now under this unitary operator, our hidden variable A equal to Z here. So that's why this 0 state, that n qubit string, this will be H tensor n Z and minus as it is. And finally here you are operating the same thing, H tensor n and I. So these two gets cancelled, that means identity. Finally you will get Zn, I mean Z, n qubit string minus. Once you make the measurement here, you will get the output as Z. So I hope you understand what is this Bernstein Vazirani algorithm. Okay. So if any doubt or any mistake is there, I request you please inform me. Okay. So thank you, and we will meet again in the next video.